So, let us start this lecture with a thought process. An inner bond among souls is the strongest among all bonds exist in this universe and is as old as our universe. If you look at in the last lecture, we basically discussed about heat of formation and heat of reaction and heat of combustion. Then we learned how to calculate the heat of reaction from the heat of formation, and then knowing the heat of reaction, we also calculated the heat of combustion. And keep in mind that we are using heat of combustion and the calorie value interchangeably, right? And we also learned how to estimate the lower heating values and lower calorie values, or lower heating values or higher calorie values, right? And if you look at, we basically determine the heat of reaction from heat of formation, right? That means those things will be available in the table. Now, suppose there is a situation where those tables or the data of the heat of formation in a tabular form or any other is not available. Let us say you are developing a new compound, right, where you know you do not have data. So, how we are going to do that is a question, right? So, for that what we will use, we will basically use the bond energy, right, and then calculate the heat of reactions. So, a question might be coming to your mind, what is bond energy? Of course, you know very well, because bond energy was taught to you in +2 very extensively. I will be not discussing about that, but I will just try to make you to recall that bond energy is basically the certain amount of energy, right, that is being used to break or form a chemical bond, right. And we know that the chemical reaction means the breaking of bond or forming of new bonds, right. Breaking of old bonds or breaking of bonds or the forming of new bonds. So, therefore, that is the energy, amount of energy which is required basically to have a bond between the elements. And you might be knowing, just now, yesterday we had Independence Day, right? We are having lot of energy, lot of money we spend for celebration of Independence Day. What for? That is basically to reinforce the bond between the individual and the country, right? What is known as patriotism, am I right? So, to have, because nowadays internationalization is there, therefore, lot of these things. Beside this also, you should have some kind of obligation for your nation. So, that is also a what you call patriotism, one form of bond, right. So, you are having also what you call bond with your family, yes or no, right. Of course, there are various forms of bonds are there in chemical reaction, covalent bond, ionic bond, hydrogen bond, kind of things. So, but how does it really form and why energy is required? Let us imagine that there are two H atom, right, and when you talk about the atom, there will be nucleus, there will be electrons, right, and these are very far apart. That means they are not interacting with each other, they will be very far apart, right. Okay. And of course, the bond is strengthened whenever there will be interaction, like for example, in ancient time the people were far apart, there is no interaction, right. For example, when I went to my engineering college, I do not have an interaction with my parents except writing a letter, but today you are having more interactions, that means more bond, is it so? Do you have better bond than what it was previously. Of course, that is a debatable thing, we will not discuss. Now, coming back to this, that this that will be having zero energy. We are considering that there is no interaction, therefore, it will be having zero energy here. And as this atom will be coming closer, right, what will be happening? That means there will be interaction between the nucleus and the electron of other hydrogen atom, and also there will be interaction between nucleus to nucleus, right. So, therefore, there will be when they are coming, there will be two forces which will be acting. What are those two forces? One is the attraction or the cohesion, you call, right. Other is repulsive forces. In this case, as they will be closer to each other, then attractive forces will be stronger, repulsive forces will be weaker, right. Until what will happen? It will be coming to a minimum level, right, which is happens to be for this, that is hydrogen molecule will be formed, because that is the lowest overall energy of the system, and the distance, of course, the optimum, right, and that distance is known as bond length, right. In this case, it happens to be 74 picometer, and the energy whatever is there is 7.24 into 10 power to minus 19 joule. It is too small energy, isn't it? It is too small energy. So, if it is there, then what will happen? Like that will be the strongest bond will be formed, like bond will be formed. In that case, like you can say that the separation distance is the optimum one, right, and this amount of energy is found. But what we will do with this? This is too small energy. But when you talk about this bond energy, is basically will be in terms of mole, right. Whenever we will talking, will be terms of moles. And you might be knowing, according to the Avogadro's number, right. What is the Avogadro's number? Is basically at 6.23 into 10 power to 23 molecules per mole at standard temperature and pressure. But what will be the volume? Volume will be 22.7 liters, right. So, what I am saying then, but we will be more interested not that a single hydrogen molecule is being formed by from the two this thing or any other things, but rather we will be talking about in terms of moles. So, the bond energy often discussed on a per mole basis. So, average bond energy for HH bond will be 436 kilojoule per mole. It is a quite a large amount of energy per mole. Keep in mind that this bond energy is will be different than the dissociation bond energy. Okay, what we will be more interested in the average bond energy, right. I will take an example of methane, right. So, let us say the methane CH4, right, and CH4, from that one H atom is being extracted. As a result, there will be CH3 and H, right. CH4 will be, let us say, getting into CH3 plus H. Then what will be the, because one hydrogen bond is being dissociated, right. So, what will be amount of energy that is required is something 435 kilojoule per mole, right. But if we will go for the next one, that is CH3 will be converted into CH2 plus H, right. Then what will happen? That will be 438 kilojoule per mole. And again similarly, if it is CH2 CH plus H, then it will be something 438 kilojoule per mole. And in the last one, of course, that will be C and H, that will be 339 kilojoule per mole. But if you take average of that, because all are CH bond, right. If you take average, what you will get? You will get something 414 kilojoule per mole. right, and that will be using, but individual is a dissociation, that will be different, right. So, you should keep that difference in your mind. And of course, the table should be available in the bond energy of various kinds of bonds, right, and those are being estimated and tabulated, and we can use that. If you look at, this is given, these are the H bond, of course there will be single bond, there will be double bond, and some triple bond are there also, various things, and these are bond length in picometer is given, and these are energy which is given, like HH 436, SC or CH, SC or CH, whatever you call, right, 414, like that it goes. And similarly CO and other various bonds are given. Keep in mind that when you use this CO2, right, and that will be, you will have to, when it is a CO2 basically CO bond, the CO2 you will have to use 799 kilojoule per mole, that is being given. So, what we will do, we can use this kind of data of the bond energies, right, and estimate heat of reaction, right, instead of using the heat of formation, where we will be using that basically when those heat of formations are not available, right, where suppose you have developed a new compound, right, where you do not have enough data, or you cannot really measure the calorific value, let us say that compound you cannot use in a bump calorimeter or a Younger calorimeter, and then find out. So, naturally you will have to use this kind of thing to check how much heat of reactions or heat of combustion is there, or calorific value of any fuel. So, let us look at 1 mole of methane is reacting with the oxygen in stoichiometric ratio, right. Determine the heat of reaction by considering the reactants to be at 298.15 and 1 atmosphere pressure. This is standard heat of reaction what we will be finding out, and we will be using basically bond energy instead of heat of formation, right. So, we know the chemical reaction will be, right, CH4 plus this is oxygen, right. So, this will be CO2 plus water, right, and this will be basically, to balance it, this will be 2, right. That means 1 mole of methane is reacting with 2 moles of oxygen going to the product of 1 mole of carbon dioxide and 2 moles of water. And now, if you look at what is CH, C basically CH4, CH4H, H, plus there are 2 O2, so O plus double bond and going to carbon monoxide O, right, plus HOH plus HOH. In this case, if you look at on the left hand side, that is a reactant side, right, how many CH bond are there? This basically 4 bond. So, I can write down CH bond 4 plus how many O bond is there? 2 O bond and the reactant side, and going to the product is basically how many bonds are there here, right. In this case, there are 2 basically 2 CO bond, right, and this is 2 HO bond, right. Now, 2 or 4, it will be 4 basically, right, this will be 4. So, now let us calculate for reactants, right, the bond energies are, what it would be? It would be basically 4 CH plus 2O. So, if you look at the table, right, let me go back to the table, the CH will be what? CH will be 4, 14, and OO, what is OO? Is 498, right, and then in the product what will be? We will be using CO2, so we will be using this one 799, right, and we will be using OH. OH is basically 464, right. So, these data we are going to put into those things, use them, and then find out what will be this thing. In this case, what will be 4 into 4, 14, right, plus 2 into 498, it happens to be 2652 kilojoule per mole, right. Similarly, for the product, the bond energy two plus 4 OH 2 into 799 plus 4 into 464, it happens to be 3454 kilojoule per mole. Now, the heat of reaction is determined as delta H R, this is basically 298 and 0, right, and this is nothing but basically reactant, right, minus the product, that is 2652 minus 3454 is happens to be something 802 kilojoule per mole. Keep in mind that if you look at earlier example, right, when we calculated heat of combustion, what is the value? Can you look at your note? Heat of reaction? Huh? Yes, that means I got something minus 803 kilojoule per mole, and that is from heat of formation, right, heat of formation. From that data I got this delta HR basically heat of reaction, we are calculating from heat of formation, this is from bond energy. So, therefore, it is very close, right, but keep in mind that it need not to be very close to each other, but there might be some difference, but that difference may be small. Here it is too small, negligibly small, but in some cases it may be 5%, 6% difference will be there, right. That means you can really calculate both the ways, heat of reaction or the heat of combustion, either from by using the heat of formation data or using the bond energy data, right. So, this is the thing what I was trying to tell you, and these things you most of you know, but only I am making you to recall and then reuse it so that you can use them in future whenever it is required. And this is basically being used when you do not have heat of formation data, then only you will use, or when it is not possible to find out experimentally. So, now to deal with this kind of chemical reactions and then associated heat liberation or heat being used in the chemical reactions, right, depending on whether it is exothermic reaction or an endothermic reaction, right, we need to use certain laws. There are two laws which we will be discussing. One is Lavoisier Laplace Law, which says that thermal energy supplied to decompose a compound into its element is equal to the thermal energy evolved during its formation from its elements, right. What it indicates? Is it related to any law, whatever you are aware? It is basically conservation of energy, that is nothing but your first law of thermodynamics, right. So, but this will be applied for the chemical reaction, and in other words what he says, the enthalpy of decomposition of a compound is same but with a equal sign that of the heat of formation, right, whenever you are having decomposition, right. For example, O, right, O and O, right, is reacting going to the O2, that means this is basically heat of formation, right, and on the back side it will be also same thing, right, that is the point what he is saying, opposite sign, right. For example, let us say that carbon is reacting with oxygen to form carbon monoxide at a constant pressure, right. Then what we need to do? I mean, we will have to basically it is balance, you can say like 1 mole of carbon is reacting with half moles of oxygen going to the carbon monoxide. Of course, keep in mind that carbon is in solid phase and the oxygen and carbon monoxide is in gas phase. And for this the heat of formation is 26.42 kilocalories, right. Of course, you must be knowing that calories and the joule, right. 1 kilocalorie is equal to 4.18 kilojoule. Basically, 1 kilocalorie is equal to 4.18 kilojoule. So, if you look at the reverse reaction, that is carbon monoxide is converted into carbon and oxygen. Then it will be same, but delta HF is equal to 26.42 kilocalories, but keep in mind that this is basically with a positive sign, that is all, right. And right. So, as I told that Lavoisier Laplace law is in agreement with the first law of thermodynamics, as it is not possible for any chemical reaction to create some energy, right, or maybe destroy it. It can only convert one form to the another, right. So, that is basically it talks about the first law of thermodynamics, and this will be in case of basically an isolated system, right. Can it be applied for other system, right? When there is a heat interaction, then it is actually, it will be converted to work or work will be converted to heat, but here there is no work, there is no heat being transferred. So, therefore, you are considering as a basically isolated system, right. So, and that is nothing but your first law of thermodynamics. So, how we use it we already know, but I am just trying to summarize it. Lavoisier Laplace law enables us to write the thermochemical equation in reverse order, the forward direction or the reverse direction, heat of reaction will be same, right. Okay. So, we will this stop over here. In the next lecture we will be discussing about another thermochemistry law, and that is known as Hess law, right. So, we will discuss that in the next lecture. Thank you very much.